back to my today's session on Law of Electromagnetics second. Myself Dr. Sayanti Chatterjee, Associate Professor of the EEE Department of IARE. So as I discussed earlier, in my last class we have discussed about the field Coulomb's law in the vector form, Gauss law in vector form, Ohm's law, continuity equation, Biot-Savart's law. Now we will start the second half of my discussion. That will start with Ampere's law, Lorentz force, Newman's formula, Faraday's law, Maxwell's law in modified form, Maxwell's law in free space, and Ponting theorem, and Laplace and Poisson's equation, that is only not discussed in my previous lecture. So this is my next lecture. We will continue from this. This is first part is over. Now we will discuss the second part. So we will start my today's lecture from the Ampere-Circuital law. Ampere-Circuital law is, so Ampere-Circuital law we will discuss today. Ampere-Circuital law we get from the modified Biot-Savart's law. Ampere-Circuital law can be written as the line integral of the magnetic field surrounding closed loop equals to the number of times the algebraic sum of current passing through the loop. Suppose there is a conductor carries a current I, then the current flow generates a magnetic field that surrounds the wire, and we can write that the surface integral of H dot dl is equal to I enclosed. The equation's left hand side describes that it is an imaginary path encircles. If there is a current flowing conductor, we can tell there is an imaginary field, and the field is the H dot dl is equal to I enclosed, and each and every point there is an H whose direction is in the radially outside. And if we take the integration, the continuous addition is nothing but the integration. So if we take the integration of the each point, we can write H dot dl is equal to I enclosed. H dot dl is equal to I enclosed. This is the Ampere's law. So you can see, if this is a conductor, current is flowing. This is the top view. So we will get, if we check the front view, this is a current carrying conductor. So there will be some circular intensity field, and the radius is r. The value is I. So we can write that the H dot dl is equal to I enclosed. So what are the applications of the Ampere's law? The magnetic field intensity in the surrounding closed path is always at the tangential at each and every point. At each and every point on the closed path, the magnetic field intensity has the same value. Determine the magnetic induction due to a long current carrying conductor. We can determine the magnetic field inside the toroid and the solenoid also. Determine the magnetic field by a long current carrying conductor, and find the force between the current carrying conductor. So these are the Ampere's law. Now we will move to the Lorentz force. So before the Lorentz force, we have to understand the force on an electric charge in a magnetic field. The magnetic field can exert a force on an electric charge only if it is moving. On the fixed charge, means if the charge is static, there is no force due to the magnetic field. So if there is a change in the magnetic field, it should feel some current. The force increases with both an increase in the charge and magnetic field strength. Moreover, the force is greater when the charge have the higher velocity. And we know F is equal to Q, V cross B, where Q is the charge, V is the velocity, and V is the magnetic field. We know the force in the magnetic field is equal to Q, V cross B. Thus, it acts as a plane and does not contribute to any work done on the charge. And the direction of the force is always determined by the Fleming's right hand rule. So, what is the Lorentz force then? The Lorentz force can be written as the if there is one electromagnetic field, so the charge will feel F is equal to if a moving charge is in a magnetic field, it will feel some electric force and it is Q into E. Similarly, the charge will feel some magnetic force as we discussed here, Q V cross B. So what is the total force? Total force is equal to Q E plus B cross B. And this equation is known as the Lorentz force. F is equal to Q E V cross B. This is the Lorentz force. Now we will discuss about the Newman formula. The Newman formula calculates the mutual inductance of a closed loop. Let us consider two circular coils as near as possible, and they are flowing. The current is I1 and I2. In the first C1, in the first closed contour, I1 current is flowing. In the second contour, I2 current is flowing. The separation between the two is R. This is the R is the separation between the 2 points, and the cross-sectional area of this is S1 and S2. So from the magnetic flux density, we know B1 is equal to grad curl of A1. What is A1? A1 is nothing but the vector potential of the magnetic field, and vector magnetic potential A1 is nothing but the integration of mu I1 dl1 by 4 pi r square. So the number of flux of the second coil, second coil due to the I1 we know is equal to B1 into ds2. The B1 is the flux density of the first coil, and ds2 is the flux, the surface area of the second coil. So number of flux cutting the second coil is equal to B1 is equal to ds2. So psi 2 1 is equal to B1 integration of total flux is equal to integration of B1 into ds2. What is B1? B1 is nothing but the grad cross A1. So what is B1? B1 is nothing but the grad cross A1. So we can also write that so what is the value of the A1? A1 is, what is A1? Integration of mu I1 dl1. So we can write psi 2 1 is equal to integration of double integration of grad cross mu I1 dl1 by 4 pi r into ds2. So we got the value double integration. So if we take the value of the mutual inductance, what is mutual inductance? Mutual inductance psi 2 1 is equal to psi 2 1 divided by current I1 is equal to M21. So what is the M21? Double integration of grad cross dl1 into ds2 by 4 pi r mu I1. So this is mu into mu. So we got the Newman's formula from here. We can get the Newman's formula for here about the mutual inductance. So what we got? Psi 2 1 is equal to A1. So double integration of, now grad cross A1 ds2 can be written as the A1 dl2. Again grad cross A1 ds2, using the Stokes formula we can write it as A1 dl2. So psi 2 1 is equal to mu I1 dl1 dl2 by 4 pi r square. So the mutual inductance is the psi21 by I1. So if we put the value M21 is equal to double integration mu, not I1 will be not there, sorry, mu, okay, I wrote it, mu dl1 dl2 by 4 pi r. Now we will discuss about the Faraday's law. What is Faraday's law? Any change in the magnetic field. So Faraday is known as the father of electromagnetism, and he has told about the three laws. The three laws are the Faraday's first law, second law, and third law. Faraday's first law tells about the any change in magnetic field of a coil or air will cause an EMF to be induced in the coil. This induced EMF is called as the induced EMF, and if the conductor circuit is closed, the current will also circulate through the circuit, and this current is called the induced current. The induced current can be done by moving a magnet towards and away from the coil, by moving the coil into or out of the magnetic field, by changing the area of the coil, by rotating the magnetic field by relative to the coil. So you can see that if there is an electric field and magnetic field, this green one is the magnetic field and the green one is the electric field and the blue one is the magnetic field. If there is a rate of change of flux, then it will induce some EMF. If it is a time varying field, so if it is moving continuously, it will induce some EMF. What is the Faraday's second law tells? Faraday's second law tells that this magnitude of the EMF in the induced coil is equal to the rate of change of flux that linkage with the coil. The flux linkage of the coil is the product of number of the coil and the flux associated with it. So we can write E is equal to rate of change of flux d phi by dt. And according to the Faraday's third law or the Lenz law, we can write E. The direction of the E will be such that it will oppose its cause. So E is equal to minus n d phi by dt. E is equal to minus n d phi by dt, and it is the Faraday's law. Now we will discuss the Maxwell's equations. Maxwell has the 4 equations, and that together form a complete description of the production and the interrelation of the electric and the magnetic field. The physicist James Clerk Maxwell in the 19th century has first tell about the electromagnetic field's fold equation, and this expressed with the experimental law. So the 4 equations are known as the respectively electric field diverges from the electric charge, and it is a modified Coulomb's law or Gauss law. There are no isolated magnetic poles, but the Coulomb force acts as the poles of the magnet. The electric fields are produced by changing the magnetic field with an expression of the modified Faraday's law. And the last one is the modified Ampere's law or Ampere-Circuital law. So, as I told, the Gauss law, first one is the modified Gauss law for the static magnetic field. Second one is the Gauss law for the static magnetic field. Faraday's law about the time varying magnetic field, and the Ampere-Maxwell's law is also the time varying electric field. So, two about the static field, 2 about the magnetic field. One is the static field with the static magnetic field, time varying electric field, time varying magnetic field. So there are 4 equations of the Maxwell's, and the total electrical engineering stands on the Maxwell's equation. So first we will discuss about the Maxwell's equation. Maxwell's equation is known as the Gauss law or modified Gauss law. we will discuss about the Gauss law or modified Gauss law. What is the Maxwell's first equation tells? We know from the Gauss law that integration of d dot ds is equal to psi electric field is equal to q. Next, again, what is q? Q is equal to rho v into dv. What is rho v? Rho v is nothing but the what is rho v? Rho v is nothing but the volume charge density. So we can write that d dot ds is equal to rho v dv, and this is the Maxwell's first equation. Maxwell's first equation in the integral form. So if we move to the second equation, what is the second equation? Here it is ds, it is the dv. So we will use the divergence theorem. So we can write grad dot d dv is equal to rho v dv. So grad dot ds can be written as the grad dot d dv rho v dv. So both sides there are dv. So we can write grad dot d is equal to rho v. Again we can write grad dot epsilon e is equal to rho v. So grad dot e is equal to rho v by epsilon. So this is the this equation, or we can tell this equation, this is the first equation of the Maxwell's in the point form. So we have discussed the Maxwell's first equation in the point form. D dot ds is equal to rho v dv. This is the integral form. And what is the point form? Grad dot e is equal to rho v epsilon, or we can tell grad dot d is equal to rho v. This is the first law. Now we will discuss about the Maxwell's second equation. From the Gauss law, if we use the Gauss law in the second equation, we can write that the psi is equal to integration of b ds. But the total flux is always in a closed surface is always 0 in the magnetic field. So we can write psi is equal to integration of b dot ds is equal to 0. So b dot ds is equal to 0. This is the Maxwell's second equation in the integral form. Now again, if we use the divergence theorem, if we apply the divergence theorem, b dot ds is equal to grad v dv equals to 0. So grad v is equal to 0. This is the Maxwell's second equation in point form. So there is some assumption. We are assuming the total magnetic flux passing through any closed surface is 0. The assumption that there are no magnetic monopoles. We are assumed that the magnetic monopoles cannot be practically feasible. No magnetic flow sources and magnetic flux lines are always closed upon themselves. There is no diverging lines are there, and also the law of conservation of magnetic flux. That number of magnetic flux pass is the maintaining the conservation of flux. Now we will go for the Maxwell's third equation. From the Ampere circuital law, we know H dot d integration of HDL is equal to I, and the current is J dot ds. So if we both equate together, we will get H dot dl is equal to J dot ds, and this is the integral form. Now, how to write the point form? We will use the Stokes theorem. So H dot dl can be written as the grad cross H. As H is an vector form, we will use the grad cross H. So grad cross H is equal to ds is equal to j ds. So grad cross H is equal to j, and this is the but J, it is only for the conductor. But in the practical case, it is the J plus JC, where JC is the displacement or leakage current density. When current is flowing in and there is some leakage current or displacement current in the medium, and this is called the displacement current density. So we can write grad cross H is equal to J plus del D by del T. JC is equals to, what is JC? JC is equal to del D by del T. D is the electric flux density. What is D? D is nothing but the electric flux density. So we got grad cross H is equal to J plus del D by del T. So what are the assumptions we are taking? We are taking that the electric current I, or changing electric flux through a surface, produces a circulating magnetic field around the path. Electric current and currents and its changes in the electric field are proportional to the magnetic fields about the areas where they accumulate. And we can write the modified form of the grad cross H is equal to J plus del D by del T. Now the Maxwell's fourth equation. In the Maxwell's fourth equation, you can see if we move one magnet, there will be a flow of current from the Faraday's law. So E is equal to minus d phi by dt is equal to E is equal to integration of B. What is phi? Phi is nothing but the B ds. So d by B ds by dt. Again, we know electric potential is equal to E dl, because electric voltage is equal to voltage is equal to E dot dl. So E dl is equal to minus dB ds by dt. So this is the again integral form. Now E dl is equal to, again if we use the Stokes theorem, E dot dl is equal to grad cross E. So grad cross E is equal to del B del T by ds. Grad cross E is equal to minus dB by dt. This is the Maxwell's fourth equation. So what are the assumptions we are taking? Changing the magnetic flux through the surface induces an electromotive force, and the changing of the magnetic field induces a circulating current. So these are the assumptions we are taking. So if we want to write it in a one form, grad cross E is equal to minus del B by del T is equal to E dot dl minus del B by del T ds is the Faraday's law. Grad cross H is equal to J plus del D by del T. This is the modified Ampere circuital law. Grad dot D is equal to rho B is the modified Gauss law, and grad dot B is equal to none. These are all for the static. These two are for the static field, and these two are for the time. First one is the electrostatics. Magnetostatics. Time varying magnetic field. Time varying electric field. So this equation is for the electrostatic, this equation for the magnetostatic. Here these two equation is for the time varying field, and this equation is the time varying electric field. So thank you. We have discussed about the Maxwell's law. The others law I will discuss in my next lecture, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.